Let's move on to what the next topic is going to be. And the next topic is going to examine what happens when we take those repeated samples from a population. And why is that so important? It's because in statistics, in public health, in statistics, that's really what we're always doing. You very rarely are in a situation where where you know the mean of a population. Most of the time, the only information that you have about a population is what you can draw from a sample from that population. So we're almost always dealing with samples. Okay, so let's take a look at this. So if I have a population, and that population has a mean of 100 and a standard deviation of let's say 10. Mean is 100. Standard deviation is equal to 10. We know empirical rule, right? We know the empirical rule just as a rough guideline. The empirical rule says that 95% of that population is between 80 and 120, for instance. Okay, so that's pretty interesting right there, right? But now we're never going to actually know that entire population. We're never going to know mu, and chances are we're not going to know sigma either. For this, for today, right, we're going to start off saying, you know, most cases, we don't want things too complicated. We're going to say that we know sigma, we just don't know what mu is. So we take a sample. I'm going to say sample size 36 again, let's say, since we brought that up. We're going to take a sample of size 36, and we're going to say to ourselves, well, what happens if I take a sample of 36 random people from this population? What can I expect to get for the average X bar, for the average of that sample, right? Well, if I take a random sample, if I just picked out one person, there's a 2.5% chance they would be under 80, and at 2.5% they would be over 120. That's one person. But for me to get an extreme value like that, I would have to get, for me to get a mean that have that extreme a value, in other words, be under 80, a mean of 36 randomly selected people, and get a mean that's so low that it's under 80, that would have to have, let's see, there's a first person, only a 2.5% chance. Second person, only a 2.5% chance. Third person, only a 2.5% chance. Remember what we did with this? 0.025 times 0.025 times 0.025. If I do that 36%, the number will be so small you won't be able to display it on your calculator. Super improbable. The number that when we take a sample of 36 people, it's likely that the average that we wind up with is going to be close to our population mean. May not be exact. Maybe I get 98 instead of 100. Let's say I do it again. Maybe I get 102. Let's say I do it again. Maybe I get 101. Let's say I do it again. Maybe I get 104. Say I do it again. Maybe I get 97. All of these are going to be closer to the population mean than is the distribution of the population itself. Just makes sense, right? That if you average 36 people, you expect to get closer to the mean than the spread for the entire population, right? So the interesting thing here is that we could take all of these numbers, as I think we did that exercise, right, with the random numbers and stuff like that. So we did that here, right? And we could take all of these numbers, we can create a new distribution, and this new distribution of these sample means, well, half the time we're going to be below the mean, half the time we're going to be above the mean just by chance. And so it makes sense that the overall mean for our samples is also going to be 100, like the population. But our standard deviation for the for all these sample means is going to be much narrower, and that standard deviation is going to be equal to sigma, this population standard deviation, over the square root of the sample size. In this case, that standard deviation is going to be equal to 10 over 36, square root of 36, which is 6, which is going to be, I won't bother to resolve it, but it's going to be about 1.67, I guess. Okay, so that is going to be our new variability. And 95% of the samples that I would take from this population are going to be between what and what? They're going to be between two standard deviations and two standard deviations above, two below, two above. In other words, about roughly 3.2, 3.3, about 3. About 7, about 90. I'm going to call it 97 to 103, but just to make it simple, right? 97 to 100. 95% of these samples are going to be between these two numbers. In other words, the probability that we would get a result from this population with a sample mean is predictable. We could say 95% of the time we're going to get something that's between two standard deviations of the sample means above and below the mean that I get for the samples, right? Just like I did before. So we give that a special name. We call that the standard error instead of standard deviation. That's the standard deviation for the sample mean. It's called the standard error. Well, that's great because I can use that information because I'm never going to take 100 samples of size 36. I'm going to take a sample from a population of size 36. And I may say to myself, well, what is my mean for that sample come up being? Let's say the mean comes up to be 98, right? Let's say I know that the population mean is equal to 10. Population standard deviation is equal to 10. Well, how can I use this information? Well, I know repeated samples of this size would give me a standard error equal to sigma over the square root of n, which is equal to 1.67. Same thing I just did right there, right? That's 10 over the square root of 36, 1.67. Okay, so that's my standard error. And I could say to myself, well, let's say I got this right, that really is the population mean. We can see it isn't, right? That really is let's say for a moment I said it's population mean. Let me see what happens if I add and subtract two standard deviations from that number. In other words, I say x bar plus or minus 2 times the standard error. Okay, what does that come out to? It comes out to 98 plus or minus 2 times 1.67. Okay, and again, 3.3 rough. I'm going to say 3.5. Let's say that comes out to 3.5 below that, which is 94.7, and 3.5 above that comes out to 101.3, right? Then I can say 90, I can say if that really is the population mean, if I happen to get it right, I would expect 95% of the time that if I took another sample, it would wind up between these two numbers for the same reason that I was able to say that this is what the distribution of this population was, okay, that the sample means were, right? However, I don't know. That's not the mean. I have no way of knowing whether it's the mean or not. So I'm going to use this differently. I'm going to say to myself, well, the fact that this came up, and I know that this is the spread here, I'm going to use this differently. I'm going to say that this, between these two numbers, I'm 95% certain that the true population mean is represented. And in fact, it is. 100 is between these two numbers. So what's the advantage of this? If I just take a sample of size 36 and I find that the mean is 36, somebody asked me, well, what'd you find out about this population? I could tell them, well, excuse me, the mean is 98. Well, the mean blood pressure for this sample is 98. So I'm thinking the mean for the population is 98. Well, how sure are you? Well, if I just do that, I can't give someone an idea of how certain this result is. But now I can instead tell them, well, I got a sample mean of 98 for my sample, but I'm 95% certain that the true population mean is between 94.7 and 101.3. So now I can identify for him a probability of where that true population mean stands. That's the power of this. Now we have a way to estimate what the population mean is, but also to predict how well we know it. In other words, whether the range is very wide or whether the range is very narrow. So I'm going to do this again. It's called a confidence interval. I'm going to use exactly the same numbers. Okay, use exactly the same numbers. I'm going to say that X bar is equal to 98. I'm going to say that the standard deviation of the population. Usually we don't know this. I'm just saying that we know it for now, so that we can use our formula, which tells us the standard error. Sample size is 36, and our standard error again we calculated as 10 over 6, which is 1.67, right? I do that so I can do that. Okay, so now I'm going to again calculate my confidence interval, my 95% confidence interval for the true population mean for mu, for what mu is, right? My true population mean is going to be equal to X bar, my mean, plus or minus my z-score, the number of standard deviations. Now, I said before 2 times, right? Because 2 standard deviations apart. Well, we know in reality that 95% of the distribution is not really between 2 standard deviations and 2 standard deviations above. It's really 1.96 standard deviations above and 1.96 standard deviations below. That's really where 95% of the population is. So instead of using 2, I'm going to use 1.96 times my number of standard errors or standard deviations for the repeated sample needs, which is 1.67. So for my 95% confidence interval, I can resolve this. 98 plus or minus 1.96 times 1.67. So let's see what that comes out to. Okay, 1.96 times 1.67 is equal to this number. I'm going to put it into memory. I'm going to clear this. 3.27. I'm going to write it down first. Oops, I made that go away. That's equal to roughly 3.27. I remember exactly what it was. 98 plus or minus 3.27. I'm going to go back here. By the way, okay, I'll come back to that in a second. Oops, clear. I'm going to clear this. Okay, so now I'm going to subtract it. I'm going to take 98. I'm going to subtract that number 3.27 from it. Minus, recall memory, is equal to 94.72. I'm going to just round that to 94.7 for our purposes. 94.7. And I'm going to add it, and it's going to come out to 101.27. Okay, I can do that in my head, I think, right? So that is my 95% confidence interval. Well, that's interesting, right? Okay, however, you know what I could do now too? Well, gee, what if I want to be, I want to be more certain that I capture the mean between these. That means that 5% of the time, there's 5% chance that it's not between these two numbers, that it's lower or higher. Let's say that's unacceptable. I want to be more certain. In order to be more certain, do I have to make the range wider or narrower? Got to make it wider, right? To get more certainty, higher level of certainty. Let's look for a 99% confidence interval, right? So how do we get that? Well, again, X bar plus or minus, and the standard, we're going to multiply by the number of standard deviations. But for a 99%, we need the z-score, which represents only half of 1% on one side, half of 1% on the other, and 99% of the output puts in between. That's going to be equal to 2.58. That's the z-score we need for a 99% confidence interval. And what if I don't need to be quite as uh, 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 accurate? Maybe I'm satisfied with a 90% confidence interval, 90% certainty that I've captured the population mean. Well, in that case, we're going to use X bar plus or minus, and instead of 1.9625.58, I'm going to use 1.64. If we get time, I'll show you on the Z table that these numbers really represent those areas on the Z table, okay, times the standard error. And you can work it out exactly the same way. In this case, 90% confidence interval is going to be what? Not wider or narrower? It's going to be narrower. Why is it going to be narrower? First of all, because you're using a lower number to add and subtract from X, right? It's going to be a narrower range, but also it makes sense. If you're willing to take more risk, you can make the interval narrower than if you were unwilling to take it. You wanted how to make it wider to get a higher level of confidence of capturing the mean. So that's how we're going to use this idea of confidence interval to help us predict what the actual mean of the population is based on the sample mean, and based on the fact that we know we're never actually going to know what mu is equal to. So that's the idea of this confidence interval. By the way, let's just take the up here where I multiplied out 1.96 and 1.67, and I said 98 plus or minus 3.27. What's a good name for this number? Plus or minus 3.27. In other words, this or this or this. What's a good thing to call that? Was adding and subtracting. How about the margin of error? Right? The name of that is the margin of error. So the margin of error is equal to the z-score times the standard error. You don't need to know that, right? Because you just need to know the way to make this thing work, right? But you could call that the margin of error. Okay, so now what I'm going to do now, which is much delayed, and is I'm going to play a video. Okay, go to Blackboard. I'm going to go to Blackboard right now. I'm going to play a video lecture so I can catch my breath. And okay, if we can leave this page. If you go to session 7, I counted last week's exam as a session. Most of this, during a regular semester, we probably don't, but we did for this purpose. And if the internet ever works, and we get, there we are, okay, 7, go over here. And you'll notice that there is a link here. Actually, it's the same one that's over here, I think. Here it is. Here it is. That link, I believe, is the same as this link. So you can play either one of them. If I click on that, it's going to play one of Levi's lectures from a previous semester on the on this topic, on this idea of the confidence interval, moving on to something called the t-distribution. Okay, so his lecture is going to get a bit ahead of what I've told you so far, but when we come back, we're going to work on that as well. So I'm going to start it from here. If you're at home, I don't know how well this is going to come across at home. So what I would suggest is that you consider. I'm going to pause the recording. I would suggest that you start that, and then I will come back and restart the recording. So I'm going to play this here. You guys play it at home, and then when it's over, we'll come back to it. Let me just start it to see how long the duration of the video is. So it's 1 hour and 5 minutes. Okay, so it's going to review sampling distributions, confidence intervals for population mean, and it's going to start, also going to introduce the idea of confidence intervals for proportion. I got my sound turned down, that's why you don't hear it. I'll crank it up.
Some really practical stuff that you're going to see over and over in the public health literature, and being able to
calculate. So we're going to listen to this here. You guys follow it online as well. Okay, and then we'll come back at the end of this. At the end of an hour, well, I'll tell you what.
Reported in any publication.
Let me just see how far I get here.
But you're right that for any two particular samples, the thing that
tell you
looks
what.
like the Z.
Let's go up to about 45 minutes in. So at about 7:50. We'll come back and we'll actually do some examples. So don't go through the whole thing right now. You go through the rest of it later on, right? So go up to what I say 45 minutes into this lecture. Okay, so go ahead and get started on that, and we'll see you at 7:50. We're back again, and I've started recording again. Hopefully you guys are back with me. Okay, I see you ready when you are there. Good. Okay. So now I'm gonna probably, as you were watching the video, hopefully you got up just about to this slide, maybe a little bit beyond this slide, where he started talking about something ugly called a t-distribution, which we're getting get to shortly. But before we get to that, let's go back and continue what we were looking at with our confidence intervals. By the way, the reason why I like doing this is because it gives you an opportunity to get another look at important material from another voice, from another approach, from another voice. So I think it really kind of nails it in a little bit. Sometimes you'll even see me put in extra past lectures from other professors or from other semesters, just as an option for you to look at to give you another shot at understanding the material. So I'm going to close this now. I'm going to open up another blank page. Okay, so one of the things that you heard there was this idea of a point estimate. Okay, and point estimate is something that represents some value that's important in a distribution. And for the most part, usually we're talking about something that represents the middle or the most likely outcome. So when we take a sample, X bar, the mean, the average, represents a point estimate for a numerical variable. When I look at a dichotomous variable, like say gender, male or female, the percentage of people that are say female, say 58 out of 100 in a sample of female, 58%, 0.58 is a point estimate. We usually show that point that the true proportion of females in the population would be P. But similarly to our numerical variable, we're not going to sample the entire population, so we may never know what P is. But we can sample 100 people in that population, and we can know that our point estimate of that P, we'll call it P cap. That's our proportion for our sample. So we have X bar and we have P cap. And you may remember now, I hope, since it's only been half an hour, you may remember that the way that we can get a confidence interval for the true population mean, which is represented by mu, and is by, using our confidence interval, 95% confidence interval, X bar plus or minus 1.96 times the standard error, where the standard error is equal to the standard deviation of the population over the square root of the sample size. Right? That margin of error subtracted and added to our X bar gives us a measure of our 95% confidence interval. Well, now I can do the same thing with a point estimate. Okay? In other words, I can say, I don't know what P is, but it would be valuable for me to know what a 95% confidence interval, some range that I can say of proportions that I could be 95% certain that I would capture the true population proportion. Similar to our point estimate for our mean for numerical variables, for our binomial or dichotomous variable like male or female, diabetes, yes or no, smoker, yes or no, any one of those. Well, our proportion confidence interval can also be calculated as P cap plus or minus 1.96 times our standard error. The only problem is that since it's a dichotomous variable, yes or a no, what are we going to do for sigma? What is going to represent our sigma? Well, the way we're going to calculate sigma in this case is we're going to say that the standard error is equal to a function of a function of how variable this is. Is it close to 50%? Is it 10%? We're going to call our standard error the square root of P, right? The proportion, for instance, with the proportion we just spoke about, 0.58, times 1 minus P over the sample size. So the bigger sample size, the smaller the standard error, similar to when we're working with standard error with a sample mean. So let me take an example. Let's say that we take a sample of 100 women, 100 randomly sampled Hunter College students, and we're interested in knowing what proportion are female, what proportion are male. So it turns out that 58 are female and 42 are males. Okay, so our P cap is equal to 0.58. Okay, so now I know that my this particular sample of 100 students, it came out, random sample of 100 students, came out to a 58% or 0.58 female. Now, the thing is I don't know. How can I quantify how accurately I really know the true proportion? Well, 58% could be maybe it's really 42, maybe it's really 60, so on and so forth. However, it would be of some value for me to be able to understand how certainly I know where the middle, where this P is located, the true proportion of all 20,000, maybe not for Hunter, but for CUNY. Let's say for Hunter, we'll probably maybe about 8,000 students, Hunter, something like that. Pretty big school downtown, right? So let's say that our sample size is 100. Let's calculate our confidence interval given that we got this result. What's it going to be? It's going to be equal to P cap plus or minus 1.96 times our standard error, which is 0.58 plus or minus 1.96 times our standard error. Our standard error is equal to the square root of 0.58 times 0.42 divided by 100, our sample size. All this is underneath the square root sign. I'll get my calculator out, and I'm going to clear everything out here first. Okay, so 0.58 times 0.42 is equal to 0.24 divided by my sample size, which is 100, is equal to this. And I'm going to find the square root of that value. That's the value that's inside the square root. I'm going to find the square root of it using a scientific calculator. And it turns out that it's 0.04935. I'm going to call that 0.049. Okay, so my standard error is equal to 0.049. Okay, so now let's substitute our standard error in here, 0.049. And now I multiply by 1.96, and that will give me my margin of error, the amount that I'll add and subtract to 0.58. Let's get that thing back again. Okay, I'm going to multiply this by 1.96, and it comes out to 0.09673, about 9.7%. I'm going to store that in memory. Store that in memory. I'm going to clear it out. I'm going to say 0.58 minus my margin of error, I'm going to recall that, is 0.48. Okay, I'm going to write that down here, 0.48. I'm just going to take the first two digits to speed things up a little bit. And I'm going to go back here again, and this time I'm going to clear that out. I'm going to say 0.58 plus my margin of error, which comes out to be 0.68. Right? I'm going to round it off, 0.68. 0.68. So what does that tell me? My sample came out 58% female. My 95% confidence interval tells me I'm 95% sure that the true p-value, the real p-value for the entire population is between 48% and 68%, 0.48 and 68. So if I were to ask you, am I 95% sure that there are more females than males at Hunter? Can I use this as evidence that I'm 95% sure that there are more females than males? What do you guys think online? You think so? Okay, what about you guys online? Everybody online saying no. They're disagreeing with you. They're right. I'll tell you why they're right. The reason why they're right is because we're 95% sure the true population mean is between 48 and 68. It could be under 50% for females and still satisfy this confidence interval. right? Had the confidence interval been 0.51 to 0.69, then you can be 95% sure that it's more male than female because you're 95% certain that the true proportion is above 50% for females, right? Here, you're not 95% sure it's above because it could still satisfy this, but be under 50%. Okay, so moving forward, we're going to look at this and use this as a way to understand what the probability is that, say, that your sample population is the p-value for your sample or mean for the population that you took your sample from is the same or different as the mean or p-value for some other population that's known. Okay, so you can actually compare two populations. So, for instance, to put that into perspective, if I told you population A, population B, you took samples from each one of them, and you found that the mean blood pressure from population A was 92. Mean blood pressure from population B was 94. And you found that the confidence interval for A, 95% confidence interval for A was 91 to 93. You're 95% certain that the true confidence interval for the mean mu, the mean blood pressure for group A, population A, was 91 to 93. And for B, you're 95% sure that the true population confidence interval was 92 to 96. Are we 95% certain that population A and B have different blood pressures? Well, look at this. They overlap, don't they? Right? So it's possible, and still satisfy our confidence interval, it's possible that both of these could have similar blood pressures. We can't be 95% certain that they're different. On the other hand, if I told you that we're 95% certain that the true population mean for A was 91.5 to 92.5, and for B was 93.5 to 95.5, well, they don't overlap anymore. So we're 95% certain that this one is different than this one. So those we can say have different population means, with 95% certainty. And this one, we really can't say that they're different, at least not with 95% certainty, because they overlap, right? So we're not really going to use it this way. We're going to do something else later on that's called a t-test. But I just wanted to introduce to you one of the reasons why we're so interested in this idea of measuring a level of confidence for a range of values. In reality, the only thing we're going to use confidence interval for is to predict what range that the true population for a population, the true population mean for it is for a population that we've drawn a sample from. That's really the only thing that we're going to use it for. But we're going to extend that into something later on. We're going to actually try to determine if there's a way that we can predict that one group is different than another group by determining what the sample means for those two groups are, Group A and Group B. So that's what this is going to eventually move into. Okay, so what do we have here? Okay, I'm going to summarize all this. When we're looking at the mean from a population, a mean of a sample from a population, and we know if we know the mean of our sample, we know our sample size, right? And we know the population standard deviation, right? We can say that we can be 95% confident, right? That the 95% confident that the true population mean, mu, is between x bar, our mean for our sample, plus or minus 1.96 times our standard error. And our standard error is equal to sigma, standard deviation population, over the square root of the sample size. And we can be 90% confident x bar plus or minus 1.64 times our standard error, and we can be 99% positive that x bar is plus or minus, that mu is plus x bar plus or minus 2.58 times our standard error. Okay. Similarly, for a proportion, if we know what the proportion is, we can get that just from the yeses and the nos. If diabetics, not diabetics, males and females, we know what our proportion is. If we have a sample proportion, we don't know our true population proportion, just like we don't know what mu is, but we have a sample population, a point estimate we call p cap. We know our sample size, and we can calculate our standard error. We calculate our standard error as square root of p times 1 minus p over n. That's our standard error, right? And then we can use that the same way. We can say we're 95% certain that the true population proportion is between p cap plus or minus 1.96 times the standard error, and 99% confidence interval can be p cap plus or minus, I did them in the reverse order here, 2.58 standard error, and our 90% confidence interval can be that p cap is plus or minus 1.64 times our standard error, right? So those are our formulas for doing all these calculations. But what did I just tell you here? What is all this dependent on knowing? It's dependent on knowing the population standard deviation. Is it any more likely that we're going to know this than we know this? Probably not, right? If we don't know this, we're probably never going to know this either, unless we sample the entire population. So what does that mean? That means when we use, if we don't know what this is, what can we use instead of that? Well, instead of sigma, what we can use instead is the standard deviation of the sample, right? Because this, now I'm not talking about the standard error now, not the standard error for repeated samples. I'm talking about the actual standard deviation for the sample. In other words, we got somebody whose blood pressure was 80, and somebody else's blood pressure was 120, and somebody else's blood pressure was 82. And the actual sample itself, the standard deviation for the actual sample itself, the variability in the sample approximates the variability in the population. Just like the mean is approximated by x bar, the standard deviation is approximated by the standard deviation of the sample. The only catch is I can do this. I can just directly substitute standard error instead of sigma that's equal to the standard deviation of the square root of n. I can do that without any conscience, any level of not raising my conscience. I can do that if the sample size is large. Now, what constitutes a large sample size? Hey, 300, 1,000, 200, maybe 100. A little bit of opinion that gets involved here. But we can all agree that if the sample size is small, right? If the sample size is small, well, now, before, when we knew what sigma was and we were guessing at mu by using x bar, when we knew what sigma was and we were guessing x bar, we were pretty comfortable because we understood the variability in the population. But now, if we have a small sample size and we see that we don't know sigma and we have to depend on the standard deviation, and that standard deviation is dependent on a small sample size, say 25, say 15, say 30 or something like that, small sample size. Well, now we have variability in predicting whether or not x bar, we're going to have like some error in x bar approximating the mean, But now we also have some extra uncertainty in estimating what sigma is. That extra uncertainty has to be made up for when we create our 95% confidence interval. And we're going to do that right now. Okay, and the way that we're going to make up for that extra uncertainty is I'm going to say that I have a situation where x bar is equal to 100. The standard deviation is equal to 10, and my sample size is 25. Actually, I'm going to make it even smaller. I'm going to say my sample size is 16. Okay, so now my sample size is small. Now, normally I would say if I had a big sample, if I knew the population sigma, I would say my 95% confidence interval could be predicted by saying x bar plus or minus 1.96 times my standard error. And my standard error would be equal to sigma over the square root of the sample size. Well, if I don't know what sigma is, if n is a big number, let's say n is 1,000, right? If n is a big number, I would be perfectly comfortable saying that the standard error is equal to the standard deviation of the sample divided by the square root of n, right? So I'd be perfectly comfortable with that because it's a big sample and it would predict it very well. But now, oh no, that's no good anymore because my sample size is only 16. So my standard error, when I try and use standard deviation over the square root of n, let's say standard deviation in this case is 16. When I try and do that, well, there's a lot more uncertainty in my standard error here, isn't there? So I got to make up for that. And the way that I make up for that, and the way I make up for a uncertainty in a confidence interval, is I trade it off by making the interval wider to make up for the fact that I have less certainty. So now I'm still 95% certain because I made it wider. Well, how much wider do I have to make it? Whoops. How much wider do I have to make it? Okay, well, that's where a new distribution comes in. Okay, and this new distribution is based on the idea that when we have different sample sizes, it's going to affect the distribution of this standard deviation. So in that case, instead of x bar plus or minus 1.96, which is the z value for 5% chance of being wrong, in other words, 2.5% at one end, 2.5% at the other, for 95% in the middle, right? Our confidence interval, 95%. Instead of using the z value, I'm going to use another value that you just started to hear about in that video, which is called a t-value or t-score, plus or minus the t-value for the level of confidence that you want. So that t-value is going to be substituted for 1.96 times our standard error, which is based on our standard deviation over the sample size. So let's give this a try. X bar is 100 plus or minus t, this t value, whatever that is, right, times the standard error. Well, the standard error is equal to 10 divided by the square root of the sample size, which is square root of 16, is 4. So this is equal to 2.5. So it's t times 2.5. If this was a big sample, large sample, or if I knew what sigma for the population was, then I would say use 1.96, the z-score, for a 95% confidence interval. Now I can't do that. I have to use a different value. Now this t-value, that t-value represents a distribution. And that distribution, normal distribution may look something like this. The t-distribution is wider because there's less certainty, right? So the t-distribution is wider. And the smaller the sample size, the wider is that distribution. In fact, there's a t-table, just like there's a z-table, and a distribution, a t-distribution for every sample size. There's one for a sample size of 10. There's one for a sample size of 11. There's one for a sample size of 12. If you can imagine, it would be very cumbersome to walk around with t-tables for every possible sample size that you could have. But fortunately, we're not interested in most of the values that would be in that T table. The T table would look a lot like your Z table, except different numbers. We're not really interested in all of those values. We're only interested in a few critical values. The value that represents a 95% confidence interval, the value that represents a 99% confidence interval, the value that represents a 90% confidence interval, which would have been 1.96 and 2.58 and so on if it had been a Z table. But now we have a situation where we have a small sample. Well, let's take a look at what it would be for a sample size of 16. Okay, so I'm actually going to find that table. I'm not sure if you have it on Blackboard, but you can certainly Google it and find copies of it in your textbook. I'm going to say Gresty T table. I think it's at least it's in either this session or the previous session that I gave you a copy of this. And I'll make sure that when I get home tonight, I'll make sure that there's a copy of it that's available as well. Here's our T table. Notice that it's different in the sense that you only need the value that represents the sample size, and that represents a 95% confidence interval, a 90% confidence interval, and 99% confidence interval. You have a few others, but it's really those three columns you're most interested in. So for our purposes, we're going to look up what T value we would use instead of Z for this specific sample size. And I'm going to go down here. Notice that if it's a really small sample size, instead of 1.96, the number gets quite large. But as the sample size gets larger and larger and larger and larger, the T value that you're going to use gets closer and closer and closer until you have a sample, an infinite sample, or really, realistically, the entire population. And what is it? The Z value is 1.96, which is what you would expect, right? So what do we need for a sample size of 16? Well, first thing I see here is that there's something up here that says the DF, or degrees of freedom. Degrees of freedom is represented. Remember when we did calculated the variance and the standard deviation earlier in the semester? Degrees of freedom is the sample size minus 1. Okay, so I'm going to go down here, and this is actually, since sample size is 16, I'm actually going to go down to 15 degrees of freedom. And I'm going to move across from there to the column that represents a 95% confidence interval, and that's going to be equal to 2.131. So instead of 1.96, I'm going to use the T value, which was the Z value. I'm going to use this T value 2.13. If I were doing a 99% confidence interval, I'd be using 2.947. If I were doing a 90% confidence interval, I'd be doing 1.753, that instead of 1.64, for instance. Okay, so 2.131. Whoops. Okay, so a T-score is 100 plus or minus 2.131 times 2.5. Oops, 2.5. Get my calculator out and just repeat what I did before. Okay, it's going to be, let's see, 2.131 times 2.5 is equal to 5.32. That's my margin of error now. Okay, I'm going to clear my memory and add that to my memory. And I'm going to clear this, and I'm going to say, okay, I'm going to subtract that margin of error from 100 minus 5.32. Comes out to be 94.7. I'm going to clear that. I'm going to do it again, 100 plus my margin of error is 105.3. So I already forgot the first number. Anybody? Oh man, it's terrible getting old. 105.3. You remember what the other one was? 94.7. Good, thanks. 94.7? Okay. Did you write that down or you remember it? Okay, good. Pen and paper. I'm glad to see that you didn't remember it either. You had it written down. You came up with it because you wrote it down. Good. Thank you. I feel much better now. So we're 95% certain that the true population mean is between 94.7 and 105.3. And this 2.13 accommodates, makes this wider, the confidence interval wider, accommodating for the fact that we don't know sigma, and it was a small sample size, and we were forced to use the standard deviation instead of sigma for this. Well, how does this impact on proportions? Well, you want to know something? It really doesn't impact on it that much, because one of the rules that we are going to use for now when we talk about PCAP is that we're only going to attempt to calculate a 95% confidence interval for our purposes for this course now. We're only going to calculate a 95% confidence interval for proportions if it's a large sample size. And there's a second rule that both sides of this PCAP are greater than 15. In other words, what would not work? Let's say the sample size is 100, right? And it's diabetics. Turns out that out of your 100 people, 10 people are diabetic, 90 are not. So the proportion of people in the population diabetic is 10%. Oh, well, that's a problem. One side of this is under 15, right? Sample size is under 15. The other side is okay. Even though it's a relatively decent sample size, I won't calculate a confidence interval for this. However, if we sampled 1,000 people and it was 100 people who have diabetes, yes, and 900 people who don't have diabetes, well, PCAP is still 10%, but my sample size is big enough to satisfy my criteria. And if this criteria for sample size is satisfied, well, then I'm not going to bother with the t-score. I am just going to say PCAP plus or minus 1.96 times my standard error. And my standard error, of course, is going to be 0.1 times 0.9 over 1,000 and find the square root of the whole thing, right? Same way we did it before. So that's how I'm going to do PCAP for that. So I'm not going to worry about the t-score there. So let's call it a night. Okay, we're actually a little overtime. We're in overtime now, as they say in football. So hopefully not sudden death overtime. So at any rate, so to make a long story short, we now have a way to describe how well we know the population mean, given that we've taken a sample and we have a sample size, and whether or not we know the population standard deviation or not. We have ways of describing what our 95% confidence interval for true proportion or true mean, our point estimate is for the actual mean itself. Okay, so there are a couple of documents on Blackboard that are in this session. Okay, let me go back here just to show you what they are. One of them is this document, this Word document, which basically gives you a rundown of all these formulas I just talked about. Okay, for the population mean, for proportion, how to calculate it, and so on and so forth, and some of the rules that we're going to observe when we're using them. Okay, so you got that document, how to calculate a confidence interval, as a reminder of these formulas.